In the last lectures, we learned diff pulling. In this lecture, we learn eigen pulling. Here, whole idea is to learn assignment matrix, where we will use spectral clustering as an approach to cluster set of node in our graph using spectral clustering. After applying the spectral clustering, we will have a set of cluster which are not overlapping, and they have a set of nodes in that particular cluster. Then the idea here is to construct an assignment matrix S in so that we can create coarsened graph. And the assignment matrix will provide certain kind of connections between the input nodes and super nodes that have been constructed, where each of these S matrix row has a single element being 1 and remaining being a 0. So, if you look at it here, this is my input nodes, and by applying spectral clustering, I can, let's say, construct a 1 cluster 1, cluster 2, and the cluster 3. Okay. So they are non-overlapping cluster, and then I can construct the 3 super nodes. Then the objective here is to go from this to this and create an assignment matrix X, which somehow allow us to create coarsened graph from the input graphs. And here we are going to use concept of Laplacian matrix and the concept of eigenvalue of Laplacian matrix to generate a pulling operation and get a coarsened graph and feature associated with each super nodes in that particular coarsened graph. So let's start with understanding each cluster. Recall that I have each cluster and I have to look at what kind of connectivity they have and create a super node out of it. So for the kth cluster, we have assumed that there are n k nodes and corresponding adjacency matrix, which we call induced adjacency matrix, AK, which is of dimension nk cross nk. Okay. So what we'll do is we'll define a sampling operator Ck, whose element is either 0 and 1, which start with some n in, which is number of nodes in the input graphs, and it has a nk, which is nodes in a kth cluster. So that's the dimension of my Ck operator, which is called sampling operator. Here, each element of this Ck matrix, Cij, let me put it here, k, which denotes the kth cluster. So Cij is equal to 1 if node Vi corresponds to jth node in the cluster. So I would have a set corresponding to kth cluster, and when I look at my matrix Ck for the kth cluster, I will define my element of Ck based on node Vi corresponding to jth node in the cluster. Okay. And for the kth cluster with nk nodes, the induced adjacency matrix can be actually obtained using the in adjacency matrix or adjacency matrix corresponding to in graph. Here we can see that we are going to pre and post multiplied with sampling operator, which samples the original input graph, adjacency matrix of input graph, to a corresponding induced adjacency matrix for the kth cluster. As I told you, CK is a sampling operator and AK is graph structure for the cluster K. Why we would like to have this graph structure, we'll understand when we try to define features for the node in a super node using the features of the nodes in the kth clusters. So I got induced adjacency matrix. Now what is next? Once we have an induced adjacency matrix, we can generate the coarsened graph, where connection across clusters in the original graph can be given by following matrix, where the A int is a intra-cluster adjacency matrix. So what we are trying to do is we want to figure it out what is the connection in a coarsened graph. And for that we are going to use another metric A int, which is summation over all the clusters in the output or in the next super nodes super nodes related coarsened graph. What we are interested in is connection across the clusters, which is A external. We are defining it, and A external is defined as in adjacency matrix minus interclustering adjacency matrix, and that will define connections across the clusters. And once I have that, I'm going to actually use my assignment matrix S to perform an operation where S transpose A external X leads to a new matrix coarsened graph connections or adjacency matrix corresponding to coarse graph, which is n out by n out, and each element has a tells me whether there is a connection between two super nodes in coarsened graphs or not. So this way we get from our A input adjacency matrix to output adjacency matrix corresponding to coarsened graph, or we can say it is nothing but coarsened graph output. Now we have to actually generate node features associated with this coarsened graph. For that, let's recall the graph Fourier transform, which we have used for a graph filtering. I'll talk about single graph signal, which we have looked at it earlier, where for each node f belongs to Rv, R of n is used, and what we are interested in is keeping the important components or amplifying the important components and removing the noise or unimportant components. And in graph Fourier transform, if you recall, we actually modulate this frequency and try to construct Fourier coefficients or obtain Fourier coefficients and try to modify the coefficient through set of element-wise filter and the eigenvectors of Laplacian of matrix G. And finally, we use inverse graph Fourier transform IGFT to reconstruct the graph signal, and we have seen an example where we try to minimize original noisy graph signal with the reconstruct graph signal to obtain a filter here through certain objective function. Now we are going to use the same idea for generating node features for given cluster. So let's see how we can do it. So graph Fourier transform for the multi-channels will be extended here. For the kth cluster with nk nodes, what we will do is we'll construct a Laplacian matrix for the kth cluster. Remember, unlike using a complete graph structure, we are using a subgraph structures which are in the kth cluster, and corresponding Laplacian matrix is Lk. And the eigenvectors for this Lk are u1 to unk. This nk should be capital. u1, u2, unk. Now we have the eigenvectors corresponding to that particular subgraph Laplacian Lk. What we will do is we are going to first filter the input filter using our sampling operator and get f in k, which is the feature corresponding to the nk nodes in a kth cluster. This is the input feature for the cluster k. And once we have this input feature for cluster k, remember this is a multi-channel. Unlike in previous slide, we discussed about a single channel, but we have seen multi-channels filtering during the graph filtering classes. So we can actually relate with that. What we are going to do is for ith node in a cluster K, the Fourier coefficients for all the feature channels can be obtained by simply multiplying input feature for the cluster K with uik transpose, where I is the ith node. Once we do that, we have our Fourier coefficients. We can perform and obtain the modified Fourier coefficients also. So we can do further filtering. Here we are ending at just obtaining Fourier coefficients. Once we have this Fourier coefficient for ith in cluster K, we can apply for all the nk nodes in the kth cluster and obtain the filtered coefficients for each node in the kth cluster. What I will do is I will concatenate all these coefficients for generating node features for the supernode by simply take a fk. So this is the feature of the kth supernode, where f1k, f2k and fk and k are the feature for individual node in the kth cluster. Now, if you think very carefully, when we actually do perform spectral clustering, we get a different number of nodes in a different cluster. And here the concatenated coefficient vector fk for the kth cluster has a different size depending on nk. For example, in certain cases, if there are 6 total nodes and 2 in one cluster, 1 in one other cluster and 3 in another clusters, then we will have correspondingly different kind of fk vector defining a supernode. That's kind of not useful to actually perform certain tasks, because we assumed when we do filtering that all the nodes has same kind of feature vectors. And hence, typically only few coefficients are used when we actually try to define features for the supernodes. As I told you, different cluster might have a different number of nodes. Hence, discarding few coefficients will ensure that all of them have the same feature dimensions. Also, one of the important aspects here is that first few coefficients are typically captures the most important information about those nodes. Hence, having a larger feature vector is not going to be much informative. So, just skipping first few coefficients for each supernode of the same size is a quite reasonable way of going forward and applying the graph pooling operations. And hence, with these two, we have a pooling operation for each input graph to obtain generated coarsened graph and corresponding node features.